Hey, Camilla.
Hi.
How are you today?
Good.
That's good. That's good.
How's it going?
Going pretty well. I have my first quiz for the quarter this Friday for microbiome.
Oh my God.
Yeah.
Good luck.
Thank you. Let's see. Screen. Okay. So, like you wanted to go over acidity and basicity?
Yeah, there's a couple. I didn't find the questions. I'm opening it up right now.
Mm-hmm.
But they have molecules and then you have to order them. I think there was like pKa, highest boiling, or that's boiling point though. Never mind. But he spent like a couple lectures on acidity and basicity, so I figured that would be good to know.
Yeah. There is a way to find out if something is going to be a stronger acid or stronger base. Um, to tell if something's going to be a strong acid or something that's a stronger acid, it's a strong acid, leads to a stable conjugate base. Right. So a conjugate base is the deprotonated acid. And there is an acronym that you could use to analyze the stability of the conjugate base. And that acronym is going to be CARIO. Right? Where C is going to stand for charge, A is going to stand for atom size, R is going to stand for resonance, I is going to stand for induction, and then O is going to stand for orbital or hybridization. So for charge, let's say that I'm going to draw in the acid in red and then draw in the conjugate base of the acids in blue. If let's say I have this hydronium ion versus this water molecule here, and I'm trying to figure out what's the stronger acid, this H3O plus or this water. So here's the thought process of that. You draw the conjugate base or the deprotonated version of the acid, draw the conjugate bases, determine and determine which one is more stable. Determine the more stable one. Determine the more stable conjugate uh base. Right. And that more stable conjugate base comes from the more acidic hydrogen, comes from the stronger acid, from the stronger acid, right? So if this is the acid that and this is the acid, to draw the conjugate base, imagine some base comes around and deprotonates the acid, right? When it gets deprotonated, we're going to get these conjugate bases here. Right. Where whatever we deprotonate a molecule, it loses a charge. It has a -1 charge. Right. So in this acid here, it had a +1 charge. +1 -1 is 0, neutral. For the water molecule, it had a charge of 0, it's neutral. 0 - 1 is negative charge, -1. Right. And from the conjugate base right here, we determine which one is more stable. Neutral molecules tend to be more stable than charged molecules. So this is the more stable conjugate base, making this the stronger acid. The reason why is because when this acid gets deprotonated right here, to get this neutral molecule here is stable, happy, and not reactive, right? It's not reactive because it's stable. And because it's not reactive, it's happy to stay in this form, right? It's not going to try to go backwards into that form right there because it's already stable. So if this is a stable conjugate base, it's going to be staying as it is, right? Making this a strong acid. Because if it's a strong acid, it's able to be deprotonated to something stable. Whereas if we look at this conjugate base right here that is negatively charged, it's less stable, right? And if it's less stable, it's more reactive. It wants to go back into this form right here. So it's going to like try to look for some kind of proton source, H+, to get protonated, right? And when it gets protonated, it goes back into that form right there, making this a weak acid. It's a weak acid because it does not want to get deprotonated and get into the unstable conjugate base here, right?
Okay.
Right. Yeah. So that's how we could tell which one's the stronger acid. That's the theory behind all of these factors. The other factor is going to be atom size. So let's say we are comparing this acid with this acid here, and I draw out the conjugate bases. Which conjugate base do you think is going to be more stable based on the atom size factor?
Oxygen, or like is that bigger than sulfur on the other?
On the periodic table, sulfur is one row below oxygen, so sulfur is going to be
And
bigger.
sulfur is bigger.
Yeah. Yeah. And negative charges or electrons, they prefer to be on bigger atoms because they give it as a more room for the electrons to move, to roam around in, more breathing space for the electrons to be more stable, right? So that would make this more acidic, right? The bigger atom, right? Okay. Now let's say we have this acid versus this acid. The first thing you do, draw the conjugate bases, the deprotonated versions of the acids, which are these conjugate bases here. Which one do you think is more stable based on this factor, resonance?
The ester?
Carboxylate.
Sorry.
Right. We don't call this an ester because there's no OR group here. Right.
Oh, okay.
This is a deprotonated carboxylic acid, aka carboxylate.
Okay.
Right. That negative charge can do resonance with the carbonyl, making it delocalized, more stable. Whereas this alkoxide ion here cannot do resonance. It's localized. Right. So since that's the more stable conjugate base, this makes the carboxylic acid more acidic than the alcohol. Right. Now for 118C carboxylic acid derivatives, this is the main one, the main factor that you're going to look at, induction. And there's going to be 3 different scenarios for induction. Let me show you those 3 scenarios, and we'll go over the orbital hybridization after. Wait, actually, I want to keep that acronym like that. Let me go down like this. Okay. So let's say I have this carboxylic acid right here. Yeah, 3 scenarios. Scenario A is going to be this. And I have, let's do it in red to keep it consistent. This is one acid, and this is going to be the other acid here. Right. Now let's draw in the conjugate bases and determine which conjugate base is going to be more stable. Okay, based on these conjugate bases, which negative charge or which conjugate base do you think is going to be more stable?
Wait, let me bring a periodic table.
Yeah.
The chlorine for the first one,
Yes. Because
bigger, right? Or no?
fluorine is smaller.
Or chlorine.
Oh, chlorine, yes. Chlorine is bigger than fluorine, right? And I think you are looking at this factor, the atom size factor, right? The atom size factor only applies to the atom that lost a charge, like got a -1 charge, right? So in this scenario here, the example that I gave you, this atom lost the charge, this atom lost a charge. So we're going to compare these atoms here for atom size, right? If we go back down here, these atoms did not lose a charge.
Would it be fluorine because it's more electronegative?
Yes, it would be the one with fluorine because fluorine is more electronegative. The induction factor here is going to be talking about the electronegativity factor. You can think of it like that. Electronegativity. Right. The atom that lost a charge is this oxygen atom right here. Right? Where this negative charge on the oxygen atom is on the same atom. It's oxygen. So they have the same atom size. So we don't look at that there. Also, don't look at the resonance factor because they both have an equal amount of resonance, right? They both can do resonance with the carbonyl. So we don't look at that factor. We don't look at the charge factor as well because they both have a charge of -1. So that's also the same. CARIO, charge, we don't look at that. Atom size, we don't look at that. Resonance, we don't look at that. We look at induction now, or electronegativity. Like Brooke said, it would be this molecule here because fluorine is more electronegative, having a stronger pull on this negative charge right here. So you get to give it as adding more room, adding more space for the electrons to breathe. So it's more stable. Whereas chlorine is less electronegative, it has a weaker pull. Right. And because it has a weaker pull, it adds less room for this negative charge, right? There's less breathing room for this negative charge. Making this conjugate base more stable. And if that conjugate base is more stable, it came from the stronger acid. So this would be the stronger acid right here. Right. So that's one scenario of the inductive effect. Let me give you another scenario here. So let's say we are comparing this acid with this acid. The first thing you do, draw the conjugate base of the acids and determine which one is the more stable conjugate base. Right. So which one of these negative charges that we just formed in the conjugate base would be more stable? Here. Right. And then you can think of the acronym here, CARIO. The charge, atom size, resonance, induction, orbital. But we're looking specifically at the induction effects here because they have the same charge, negative charge. They have the same atom size because it's the same atom, oxygen. They have the same amount of resonance. Now we're looking at induction effects here.
The double bromine?
Yes, the double bromine, because you could think of it as like these bromines here have the same electronegativity because they're the same atom, bromine, right? But the double bromine here has double the power because it has two of them, right? Two against one, 2 wins. So there's twice the amount of induction effect in that one right there, whereas this one has half of it, right? So this one is more stable because it has more induction, more electronegativity. Nice, nice. Okay. So that's the second factor. Let's look at the third factor of induction. Let me label this as well. The first factor was looking at how do I want to say this? High En versus low En. This one's gonna be talking about number of En, high number of En versus low number of En. Same, the same En. Same. Right. Okay. The third scenario, say we are comparing this acid with this acid right here. Okay, now let's draw the conjugate bases and determine which conjugate base is more stable. Right. Okay, which one would be more stable and why?
The fluorine that's closer.
Yes, the fluorine that's closer, because it will have a stronger effect if it's closer. It has a stronger field to pull in the negative charge by induction, whereas the fluorine that's farther away has a weaker pull. That's right. So that would make this the stronger acid. And this third scenario here is talking about close distance versus far distance. So induction, there's 3 subcategories of it. Okay. Now let's move on.
That's closer. Oh, the one that's closer would be ortho, right?
Oh, right. So you're thinking of ortho meta para. That applies for benzenes.
Oh, okay. Okay.
Uh-huh.
Sorry about that.
No, it's okay. It's okay. If this was benzene, then that would be ortho. Well, it needs to be like a 6-membered ring, but this would be the first one, so that would be ortho if this was a benzene. This one, if it's two-way, that would be meta, and then here there's no para position because there's no third carbon away, right? If this was a 6-membered benzene ring, then we would have ortho, meta, para, like that, right? Mm-hmm. Yeah. Now, the other scenario is orbital or hybridization. What this factor is talking about is the S character. Think of it as the S character. So we could either have sp3 versus sp2 versus sp. So for sp3, there's one s orbital out of 4 total orbitals that are hybridized together. One s orbital out of 4 total like orbitals hybrid together, like 1s plus 3p, is 25% s character. For sp2, there's one s out of 3 total orbitals. That's 33% s character. For sp, there's one s orbital out of 2 total orbitals, which is 50% s character. The more s character an atom has, the closer the electrons are to the nucleus, right? And do you guys remember what subatomic particles are in the nucleus, like electrons are in the orbitals, what are in the nucleus? And what charges do they have?
Sorry, can you repeat that one more time?
Yeah, what if electrons, like in an atom, let's say this is the nucleus right here, and these are like the electron shells. If the electrons are in the electron shells, right? What subatomic particles are in the nucleus, and what charge do they have?
Oh, the protons and neutrons. Sorry,
Yeah.
I missed your question.
Yeah. It's okay. It's okay. Protons and neutrons. Right. And protons are positively charged. Neutrons are neutral. So you could think of the nucleus as positively charged. So do you think electrons would be more stable, more or less stable on an atom that has more S character? Right. Electrons will be more or less stable on an atom with more S character. Right. Which one would it be? More or less?
Less? I don't remember what S character looks like, but
So if an atom has more S character, right? More S character right here, it means that it's closer to the nucleus. If it's closer to the nucleus, which is positively charged, would electrons want to be close to the positive charge, or do they want to be far away from the negative charge? I mean, positive charge.
repel. Oh wait,
Uh,
no, sorry. Sorry, they'll be good.
Yeah, it would be good because opposite charges attract, right? Negative charge and positive charge attract, so they want to be close to each other. That means that electrons will be more stable on an atom with more S character, right? So based on this concept, let me give you different acids, and I want you to determine the stronger acid. Right? Let's say we have this acid versus the acid. What would you do first to determine which one is the stronger acid? Like what do you think of when you're trying to determine which one's the stronger acid here?
Do we
What's the
conjugate base?
Yes, draw the conjugate base face. That's right. So the conjugate bases of these acids would look like this. When we deprotonate the pink hydrogen, we are going to get these conjugate bases right here. So we have a negative charge on this carbon versus a negative charge on this carbon. Which negative charge do you think is more stable? Which atom has more S character?
The triple bond?
Yes, the triple bond. That's right, because the triple bond is what hybridization? What hybridization does this carbon have right here on the triple bond?
SP?
Yes, sp. That's right. Whereas this double bond has a hybridization of
SP2?
yes, sp2. That's right. And we said sp has 50% S character, whereas sp2 has 33% S character. Right. That means that the negative charge here is closer to the nucleus, right? It has it's more stable because it's closer to the positive charge, whereas this negative charge here is farther away to the nucleus because that's less S character, right? Making this the more stable conjugate base, which came from the stronger acid here, right? But for 1AC purposes, you'll be more tested on the induction effect. These three scenarios here. right, with the carboxylic acid acids. Right. Any questions on that? So let's look at some Fahrenheit specific problems on this. Can you send me screenshots or upload to your drive the homework problems or practice problems that Fahrenheit has for these acid reactions? I mean, concepts problems.
Yeah, one sec.
Okay. So strong acid, first thing you do, look at the conjugate base, deprotonate the acid that you're looking at, and then once you have the conjugate base, determine which conjugate base is more stable using CARIO. CARIO. Right, CARIO. Most likely induction and electronegativity for carboxylic acids. It's the same for, like, if you're determining which one's the stronger base, you look at the conjugate acid instead and see which one's the more stable conjugate acid, which would come from the stronger base. Right? It just reversed. Okay. Let's see. Got it. Okay. So they're asking for you to rank molecules in terms of pKa, highest pKa, lowest pKa. And they give you Cl, CH2, CH2, COOH, Cl, CH2, COOH, CH3, CH2, COOH, Cl2, CH, COOH. Okay. So I don't like looking at molecules in condensed formula, so let's convert them into bond line formula. Right. Cl, CH2, CH2, COOH, whenever you see COOH, or even CO2H, that's carboxylic acid. Right, CH2, CH2, carboxylic acid, Cl, CH2, let me do it this way. Carboxylic acid, CH3, CH2, carboxylic acid, Cl, Cl. Okay. So these are the acids in bond line form. First thing you do, draw the conjugate bases, right? Imagine some bases around to deprotonate the carboxylic acid to get these conjugate bases right here, the carboxylate. Then we look at which conjugate base is more stable using CARIO. CARIO. So C stands for the charge. Neutral charges are going to be more stable than charged molecules. All of these conjugate bases here are negatively charged. They have the same charge. So we ignore that first factor. A stands for atom size, and the atom size of the atom that lost the bond, right? And the atom that lost the bond is oxygen for all of these molecules. Since they're the same atom, they all have the same atom size, right? Oxygen. So we ignore that factor. Then we look at resonance. This negative charge on the carboxylate here can do resonance with the carbonyl, but all of them can do resonance with the carbonyl. All of them have a carbonyl that they can do resonance with. So we ignore that factor. Now we look at induction, right? And there's 3 scenarios for induction. let me say this is A, B, C, D. Which one do you think is going to be the most stable or most acidic based on the induction effect, induction factor? Which negative charge is more stable?
D.
Yes, D, right? Because it has the most amount of electronegative atoms. Like all of these electronegative atoms are chlorine, right? They're the same electronegative atom. So now we have to worry about the number of chlorine atoms and the distance of them. D has 2 chlorine atoms, and it's the closest, right? It's comparable to B, like they're the same distance, but D beats B because D has 2 times the amount of chlorine, right? So D is going to be the most acidic carboxylic acid. And if it's the most acidic carboxylic acid, it's going to have the lowest pKa. Oh, wait, hold on. No, highest pKa. Wait, is it highest or lowest pKa? I think highest, because if you, yeah, highest pKa. Wait, let me double check this biochem thing. More acidic, higher or lower pKa? It should be higher pKa, but let me double check. pKa. Oh shoot, lower pKa represents a stronger acid, higher pKa, and they can say weaker acid. The higher the value of the pKa, the weaker the acid is. Weak acids are relatively higher Ka, lower pKa values. Lower Ka or higher pKa values. Smaller pKa, stronger acid. Okay, so here's another conceptual thing. Strong acid, stronger acid also means lower pKa. And then you'll see this in biochem if you haven't taken biochem yet. Weaker acid is high pKa. Okay. So since D is the strongest acid, D will have the lowest pKa. Okay, what would be the second most acidic molecule?
B.
Yep, B, that's right. And then it would be
A.
Yep, and then C. Try submitting that and let me know if that works.
Yes, thank you.
Okay, yeah. So I know why I just remembered why stronger acid has a lower pKa now, which relates to the pH environment solution. But that's more of a biochem thing, so we don't have to go over that. Just know that the stronger acid has a lower pKa and the weaker acid has a higher pKa for this question. Right. Okay. So let me see the other problem that you sent me. Boiling point. Okay, so this is talking about boiling point, which is basically the amount of energy in the form of heat or temperature. Like if you increase the temperature, you increase the heat or energy, right? To break all intermolecular forces and boil the molecule, right? Because if you break all intermolecular forces, you're gonna convert the molecule into a gas, right? All intermolecular forces are gonna be broken, so you're gonna convert it into a gas. Okay. And the intermolecular forces are gonna be van der Waals forces, dipole-dipole. Wait, let me make this the third one. Dipole-induced. But the important one that we're worried about here are H bonds, hydrogen bonds. And H bonds are when hydrogen is bonded to one of these three atoms, FON, fluorine, oxygen, or nitrogen, right? So the more H bonds a molecule has, the higher boiling point it will have, right? Because the more intermolecular forces a molecule has, the higher boiling point it will have. Because there's more bonds that we need to break, more intermolecular forces that we need to break to boil a molecule, increasing the boiling point. They gave us benzoic acid. This one, benzaldehyde, and toluene. Okay, let's draw this out in bond line form. Okay, so which one of these do you think is going to have the highest intermolecular forces? A, B, C, or D? And here are the intermolecular forces here. Like, which one will have a stronger intermolecular forces, I should say? And then did the question ask? Yeah. Question is asking highest BP, lowest BP.
A.
Yes, A, right? Because we see A, there is a hydrogen that is bonded to one of the three atoms I talked about, FON, right? There is an H bond that can happen here. So that's the strongest intermolecular force, making that have the highest boiling point. Right, A. Okay, next one. Oh, so B, notice how B also has H bond, right? Because this hydrogen is also attached to that oxygen. So B also has an H bond. But this A right here also has dipole-dipole intermolecular force because there's more partial charges, right? There's a partial positive charge on that carbon, partial negative charge on that oxygen, which can do dipole-dipole interactions with other carboxylic acids floating around. So A has H bond and dipole-dipole, whereas B only has, oh, and like everything will have van der Waals. Let's say VDW. B has H bond and van der Waals. Okay. So B would be next. And then what intermolecular forces would C have?
Hydrogen.
Yeah, so hydrogen bonds, be careful. It is bonded to one of these three atoms, FON, fluorine, oxygen, or nitrogen. we do see this hydrogen right here that is explicitly drawn out, but that hydrogen is bonded to a carbon atom, C. Right? It's not bonded to fluorine, oxygen, or nitrogen, so there's no H bond in this molecule. Right? Do you have any partial charges in this molecule? Like any partial positive, partial negative charges?
There's a the carbonyl.
Carbonyl, partial positive on the carbonyl carbon, partial negative on the carbonyl oxygen, creating a DD, direct dipole bond, and also VDW, van der Waals. Right? So C would be the third highest. And then D, there's no H bond, there's no partial charges. It's just hydrocarbons, right? No, like there's just like carbons and hydrogens everywhere. So it's just van der Waals, right? The weakest intermolecular force, making that have the lowest boiling point, right? Because it doesn't require that much energy to break those van der Waal interactions. So it should be A, B, C, D. Wait, let me make sure if that's the order that they give you it in as well. A, B, C, D. Yeah, try that and let me know if that works.
Thank you.
Yeah. Okay. Oh yeah. Let me go over that problem that you sent me last night. The 8-step weird problem. Wait, actually no. Let's do the other one you sent me first. Where is it? This one. Okay. So this problem here that you sent me, they gave us this molecule. Plus this molecule reacting in acidic conditions, H plus, and they asked us to complete the major organic product of the following reaction. No R denotes the rest of the protein chain where this cysteine residue is attached to. This homework is including like some biochem concepts, but that's good because this is a good foundation for that class. A portion has been pre-drawn for your convenience. So did you change anything of the pre-drawn structure that they gave us for reference?
No.
Okay. So this is the pre-drawn product for reference. Be sure to draw both the dashed and wedged bond on the stereocenter. The R and coenzyme A inputs can be found in the groups menu. Okay. Let's see what this is talking about here. Okay. Wait, hold on. I'm trying to figure out like what this is trying to do. Like I've never seen this co-A in like I've seen it in biochem, but in chem I haven't seen that before. So this is saying this is weird. Cysteine residue. S plus. Okay, amide, thiol. What is this? Maybe proteinate. Oh, enzyme. S. Let's make a bond here. And it's gonna be oh. Okay, try submitting this molecule. Let me know if this molecule works. This is my guess for this product, since I haven't seen coenzyme A in reaction, but let's try this one, and if it works, I'll explain the mechanism behind how I got there.
Okay, give me 1 second. It's good.
Oh, like it worked? Oh my god! Let's go! Okay. I'll show you my thought process on that. Okay. Have you taken biochem yet, Camilla?
No.
No. Okay. So, there were a lot of like biochem vocab thrown on this problem, like protein, cysteine residue, amino acid, coenzyme A, the CoA. So those are like all biochem stuff. Like you don't have to worry about that for OChem, except the protein part, which is the N118C. But I try to ignore all that distraction and just like stick to what you are learning this chapter for this midterm for 118C, which is the carboxylic acid derivative chapter, right? And you know how this midterm is talking about nucleophilic acyl substitution reactions, where I'm going to show you a general mechanism in acidic conditions, right? In acidic conditions, because they did give us acidic conditions on the arrow. If I have some kind of carboxylic acid derivative, it could be anything. That LG is just representing some random group for the derivative. If it's a halogen, it's an acyl halide. If it's a carboxylate, it's an anhydride. If it's an OR group, it's an ester. If it's an amine, then this would be an amide, right? If you put that under some kind of nucleophile, and it's usually coming with a hydrogen as well in acidic conditions, H+, do you remember what the first step would be if we have acidic conditions? Like, what do you look for if you have an acid? What's the first step?
The oxygen takes the hydrogen.
Yep. Oxygen takes the hydrogen. And what did that do? Like, what's the point of that step?
We move the double bond up.
Yes. It would do that in the background. Just think of that in the background. And if it moves up to utilize this oxygen here, this carbon will have a positive charge. So
When then the nucleophile attacks the carbonyl.
yes,
Yes.
file attacks the activated electrophile carbonyl. This first step here activated the electrophile. It made this carbonyl-carbon have a bigger partial positive charge, right? And that's a stronger electrophile now. We made a strong electrophile, which allows this weak nucleophile to attack and pop the double bond onto the oxygen like that, right? To give us this tetrahedral intermediate, OH, and then the nucleophile here, H, positive charge. Now this is the deprotonated group you want to keep, protonate the group that you want to kick out, step. So some kind of base like HSO4 minus will deprotonate the group we want to keep. So it becomes neutral, bad leaving group. And then we are going to protonate the group that we want to kick out to make that into a good leaving group with a positive charge. Once that's in place, to kick that good leaving group off, we do the two-step thing. We form the carbonyl and then kick out that leaving group that we just formed to get this intermediate here. Right? And the last step is going to deprotonate the positively charged oxygen to give us our final answer. Right? Where we see that we substituted this leaving group with that nucleophile right there, which is why it's called a nucleophilic acyl substitution, right? We're substituting the leaving group with the nucleophile that's attached to the acyl group, the carbonyl group. So this is the mechanism in acidic conditions. Any questions on this?
No, I think I'm good. It makes sense. It's a lot from like 118B.
Right, a lot from 118B. And this follows like the Fischer esterification, trans-esterification reaction mechanism as well in acidic conditions, right? Like when we went over that mechanism, it's the same exact thing, but this is more general, right? Which can be applied for this this monster here, right? Where another thing too is that, let me okay, so we have strong acid here, the H plus. But we have 3 carbonyl oxygens that we could protonate. 1, 2, 3. These carbonyls here are carboxylic acid derivatives. This is an amide. This is an amide. This we did not learn about. Right? Because we learned about acyl halide, anhydride, ester, amide, and nitrile, right? But do you remember the factors that determine the reactivity of carboxylic acid derivatives? Like what makes a carboxylic acid reactive? Like there's 2 factors that we use to determine the reactivity of derivatives.
I don't really remember, but it was something about like the conjugate base.
Yeah, the conjugate base or the leaving group ability, right? Like
Yeah.
if the leaving group leaves and it's more stable, it makes the derivative more reactive. So if we compare like these, like if they left with a negative charge, which negative charge do you think is going to be more stable? The negative charge on a nitrogen or the negative charge on a sulfur? Which one is bigger? Right, on the periodic table, sulfur is going to be below nitrogen.
Okay, cool. I had to pull it up.
Yeah. So sulfur, since it's going to be bigger, the negative charge on the sulfur is going to be better, more stable, right? So if that's the case, which one is the most reactive derivative? A, B, or C?
C.
Yes, C. That's right. That's right. C. So that's how I chose to protonate this carbonyl oxygen with the H plus like that. And then we continue with this whole mechanism, right? Where you know how to the shortcut is to like just substitute the leaving group with the nucleophile to get to the answer right away. Instead of doing the whole mechanism, this, wait, I'm gonna erase these ones here, right? Because we know now that the leaving group is gonna be this. This is gonna be the better leaving group. The nucleophile then is this whole group right here. That's gonna be the nucleophile, right? this is going to be the electrophile, and this is going to be the leaving group. So this is the whole nucleophile here. This is the electrophile with its methyl group, and this nucleophile here substituted this SOCOA, right, which is now this whole molecule here. Right.
Okay, I mean, I get what you did below.
Uh-huh.
Your
like
that makes perfect sense. It's just that yeah, it's huge. I don't know.
this one right here, like why I chose this as the leaving group.
Oh no, that's fine. I'm not quite sure how it connected.
Oh, how it connected, right? So do you get how the shortcut works here? Like how to get to this product, I substituted this nucleophile with this leaving group right here.
Yeah.
Yeah, so I'm basically doing the same thing, but the nucleophile is just huge, right? This whole thing that I was circling green, green is the nucleophile, right?
Okay, and you just switched it?
And I just switched it with the leaving group. The leaving group is now gone.
Okay,
Right,
gotcha.
but notice how the leaving group is attached to this pink carbon that's attached to a acyl group and a methyl group. That's this pink carbon here with the acyl group and methyl group right there. Right.
Okay.
But it's like rotated differently. The molecule's rotated differently. It's rotated like this.
Okay.
Yeah, right. I can show you the mechanism quickly for this right here. Right, because this is gonna be more specific, but that's how you predict the products like in the shortcut manner. So after we protonate the carbonyl oxygen, we activate the electrophile, which is going to give us this. Right. Once this is activated, this sulfur here is going to attack this carbonyl carbon, pop it up there to give us this tetrahedral intermediate. Sulfur attached to H, positive charge, that whole bulky group. And then this is COA. Now this is the proton transfer step where we deprotonate the group we want to keep, which is this whole group, and then protonate the group we want to kick out, which is that group. I'm going to do this in one step, kill two birds with one stone, but for Farhat, do it one at a time. Deprotonate the group first, and then protonate the group afterwards, right? Like how we did earlier here in the general mechanism. But I'm going to do it at the same time. Which is, I don't know if it's allowed for Farhat, but it's allowed for your helix and leavens. Okay, and then we form the carbonyl, kick out that leaving group, two-step O, H plus, and then sulfur, boom, boom. And then that's the final product. Oh, wait, no, not yet. This is the leaving group right here. But you don't have to include that in the answer. The last step then would be to use the base to deprotonate this positive charge oxygen to give us our final answer here. Right, so it's basically following the same exact mechanism as what we did here, but the nucleophile was just very big, and the leaving group was like very weird as well with the CoA. Right, but it's the same thing. It's just like weird, bulky, and biochemy groups.
Yeah,
Right.
I'm just hoping his exams aren't like that.
Yeah, I think the homework will probably be harder than the exams. I'm hoping. So I don't think he'll include big biochem molecules like this, amino acids like this.
Oh,
I hope so. I hope so. I don't know how fair it is, but let's hope.
actually,
Yeah, but this worked, right? Like when you submitted this, it was correct.
yes, yes.
Yeah. This is nucleophilic acyl substitution in acidic conditions, like Fischer esterification, transesterification, but this is some other reaction. It still follows the same general mechanism.
Okay. Thank you so much, Brian.
No problem, Camilla.
I'll probably see you tomorrow.
Yeah, I'll see you tomorrow.
All right, then. Good night.
Good night. Hey, Ryan.
Hi, Brian.
Hello, hello. You know how I said that I was gonna stay up late last night? I just went to sleep. Like I couldn't do it.
At what time?
Like midnight one-ish, like 12:01, I think.
I
Yeah.
also wanted to sleep at that time.
Yeah. It was too hard. I was too tired. We were
Mhm.
both tired.
Yeah. I think I slept like 1:30.
Yeah. 1:30.
Hmm.
You have a final tomorrow, right? Wednesday? I mean Thursday?
Yeah. There's a district assessment, and then there is also a U.S. history test, 90 questions.
90 questions. Are you ready?
I've been like writing Q&A, like flashcards for
Mm.
history.
That's good. They provide a study guide for that too.
There's a study guide, yeah.
That's good. That's good. Yeah, that's good. So you know exactly, like hopefully exactly what's on the test.
Uh-huh. Uh, uh, I've been feeling kind of down lately, you know?
What happened?
I'm hella tired. Not tired.
Oh.
I like slept a lot earlier than I thought I would. But
Mm-hmm.
honestly, it's just like, does it really matter what I get, like my grade wise, like what I get?
Um.
Like I feel like I'm gonna do okay.
Uh-huh.
My grade's not gonna change. But it's just like, hmm.
Like, is it that important that you are perceiving it to be as right now? Probably not.
Um,
Like, you're probably like putting it like way up there, but that's like maybe causing you to burn out, maybe.
yeah,
Uh-huh.
basically.
Mm-hmm. You feeling burnt out?
Yep. There's
Yeah.
no other way to describe it. So,
Like you've been feeling down.
yep.
After this week, be sure to like don't do anything school related. Get a lot of rest, spend time with friends, family. Like you might want to like stay ahead or like review some stuff, but don't do anything school related so that you get your like
Energy back and like
energy and
commitment.
mental capacity back
Mental
and
capacity.
um rejuvenate, you know.
Yeah.
Yeah, because I've been there too. Like I've stressed about school a lot. um Slept late, woke up early, um and then I lost motivation at some point because I didn't want to do anything anymore, and that's when I burnt out and lost energy, lost motivation to do things, you know.
Yeah.
Yeah. Yeah.
That's good.
Mhm.
All right. Just 2 more days.
Yeah, final push, and then after that final push, be sure to rest well.
Yeah. Hmm. Let's see. I'm just like in my room all day. Like I don't even like see the sun or anything after school.
Yeah, that contributes to that like feeling too, like not seeing the sun outside, not being connected to nature, like just staying in your room.
I'm just here all day. I
Yeah.
just took like a 3 hour nap. Hmm.
Yeah, your body like needed it. Probably, huh? Like you felt like um
Like if I sleep now, I'll like be more rejuvenated.
mhm.
But it's just, let's see. I still feel the same way, but less tired.
That's tired, right? Like you feel like it's not like like a body issue, it's like a mental issue, right? Like
It's a
you're
mental-
you're feeling down, like losing
Yeah.
motivation wise,
Uh-huh.
energy.
Yep.
Yeah, it's the burning out thing.
Uh, oh yeah, I forgot to tell you. I have this group project in AP Link. I don't know if I told you yet, but basically everybody is assigned like a topic, and like the topics are just like things that people can debate on. It's not like anything like serious, but it's like things that are like interesting. Like should schools like have like make one club per student mandatory, or like one club or sport per student that they have to like do. And like and basically everybody has like 3 people, and like I'm the only person in my group.
Oh, really?
Yeah. It's like one person is transferring schools. One person has
Uh-huh.
been absent for 2 days, and then like I don't know if they're gonna be here like at all. So I'm like the only person who's working on it.
Oh shoot! So like they're like carrying your group. You're doing all the work.
No, like one person is just leaving, so they're not working on it.
Oh yeah. They're not part of the group anymore.
Y- The
Does the
part
teacher
of the
know
group,
that though?
yeah, they at start when they first assigned this assignment in class, they told the teachers like I'm not gonna be here at all.
Oh my god.
And then
So
when someone else is absent,
uh, so did your teacher do anything to accommodate for that for you?
well, she's also absent. She was also absent today. So like, I'm hoping that that she's gonna come like for finals, because like she's my third period. So yeah,
Dang.
we had a sub today for that class. Yeah. I'm arguing against why students shouldn't like have a club, or like a mandatory club or sport to be a part of. Like, and like I'm just thinking, I don't know. This is like not like, I guess it's not like that school related, but just like it's better to talk about something else in this moment.
Mhm.
So, like, what do you think?
Um, like talking about something else besides your original idea. Or sorry, what was that? Sorry.
Like students. Okay, I just pull it up. It'd be
Uh-huh.
easier to talk
Yeah,
about.
you can share screen.
Let's see. Debatable topics. All right. So, students should be required to join at least one school, club, or sport.
Hmm.
What are your thoughts on that?
Students should be required to be involved in one school, club, or sport. Um, I don't think that should be a requirement because every student has like different lives at home. Like you don't know like what they might be going through. Like if they have like a job to go afterwards, or like if they need to like take care of like a family member, or something like that, and they won't have the time commitment to join a school or club. But if everyone does have the time to do that, then I think that would be beneficial to make the student body more diverse and well-rounded, like not just focus on academics. Um, and then everyone can like learn something from one another, especially if they join different clubs, different meetings, different sports. Um, right. So the main benefit would be like the well-roundedness part of it, but I don't think it should be a requirement because people have different like lives like that they can't control over. You know.
Ye- Yeah, I would also agree with like that statement, because I'm like on the um I'm against like that, like I'm debating against that.
Yeah.
And like
Against, I'm
and
against
like the
it.
group that is debating pros is like, I don't know, like a three, like they're all working together, and I'm like only one working on it.
So it's a 3v1 on that debate.
Yeah, it is. And
Oh
we
no.
have to get up. We have to get up and we have to debate in front of the class.
Oh my god. So you have to like come up with different points. What points do you have right now against it?
I have like a lot of points, but like I was just like blurting everything, and I was kind of mad. So like I write better when I'm kind of angry.
Oh, you write Reddit when you're angry, not when you're like calm.
No, it's just like yeah. I'm just reading everything, you know. So just like having extracurriculars outside of school are in some way or place where a student can express how they feel. However, students who have responsibilities
Mm.
at home or aren't willing to participate shouldn't be forced to join because the school made it. First of all, I think that schools should not force students to join anything. Schools are seen as facilitators of learning and excitement and should allow students to like make their own choices. If a student does good in a class with a bad teacher, that means that student is a good student regardless of what teacher they have. I don't think that the student district should enforce policies upon children to make the student more well-rounded. It should be the student's choice to make. If you force people all people into the same box and expect them to get along despite differences, there are always people who don't feel like they belong, even though school takes up most of the students' time and enables them to interact in and outside of class. It doesn't matter if there isn't a club that the student could go relate to. I think it all depends on interest. Schools can't force students to become interested in something. The interest has to come from the students themselves.
Wow, that's good. Um, dang, you like touched on like the points that I talked about and even more too, like the relatedness, the interest and everything.
Yeah, because I actually feel like I feel like that. I can
That's
I can completely relate to like the
mhm.
opposite. I mean the other person against meaning.
Right. But you're involved in water polo and like some other club too, right? At school.
Yeah, but it's like it has to do with interest. And like I
Interest, I
actually
guess you're interested in that. Yeah.
yeah, and it's actually fun and not
Right.
like stressful where I have to memorize anything like
Mhm.
science Olympiad.
I know, because if you're forced to do it and you're not interested in it, and it will be like torture.
There's a competition. Like I also like wanted to like touch on like I didn't like get to it yet. I was
Uh-huh.
just blurting out random things, but I also wanted to talk about like casual and competitive.
Yeah. Like that competition makes things like more fun and it drives you to become better, you know? Um,
That's true. Also,
yeah. Uh-huh.
mm,
Like some people say, um, like comparison is the thief of joy, but sometimes comparison can inspire you to get better, you know, like keep you
two.
accountable and like see like that's something I could compete for, and it gets you going, it gets really you going and inspire you. It's all about your mindset, you know, like instead of like
Yeah,
feeling down about it, you could be inspired by it and work towards something that you want, you know,
yeah.
that you got that you see from others.
hmm Yeah, that's where I am right now. I'm like a lot of people are doing better than me, but honestly, I just like I'm trying not to do that, and then also like I don't know. It's
And
just
it's
like I
also your values too, like what you perceive to be like good or bad, and like what you really want, you know.
mhm.
Mhm. Yeah, that's good, bouncing off ideas.
Yeah,
Brainstorming.
let's see. Number two would probably that's like that was my first reason because like I have to like have like what and like a subclaim explanation, additional evidence, and then a discussion, and then there's like a second one which is like a subclaim one, subclaim two, and then counter argument.
And counter argument, yeah. And then your counter argument was like I heard the word well-roundedness in there, so you argued against that counter argument.
Yeah. Hmm.
That's
I'm like
good.
thinking like the difference between like a club and like a normal class, like, and I'm just thinking like what do classes have that clubs don't, or like what do clubs have that classes don't.
Hmm. So classes and clubs, they could have regular time meetings. That's one similarity. The differences, class, there's more responsibility because you're graded on assignments, tests, and things like that. Clubs is like less responsibility, so it's more of like you get out of what you put in. You put more into the club, you get more out of it. The same as for class as well, but there's like an actual grade on the line. Whereas for club, like there's not like nothing on the line. Well, usually.
Mhm.
What else?
Let's see.
And in club, if the student decides to go there themselves and they're interested in it, then they will have an easier time like learning in that class. Whereas in a class, if the student does not want to be in that class and not interested in the subject, but is like forced to or required to be in that class to graduate, then the learning process is going to take longer than
Learning process, yeah.
yeah, would take much longer. It's going to be considered if the student is not interested in the material. Whereas in club,
Mhm.
if the student is interested in like what the club is about and they decide to go there themselves, they have like an intrinsic motivation to learn,
It's
which increases
yeah.
the learning process speed.
Mhm. I did two things. It's either that like the only reason like a person would join a club would be like based on interest, or like they
Mhm.
have friends like also interested in the same club, but maybe they don't have the same interest. But like I kind of like I think I touched upon like people who like didn't have a interest in the club. Like okay, let's
Mhm.
see.
Right. And
I just
also,
need
you
to
could also say like one of the other arguments that clubs be required is because if a student joins a club out of that requirement and not based on their interest, then they would not benefit as much. You know, like they're just there to be there. They're not there to learn um and learn. You know, so
I
you could
mean, they have a free choice in what club they want to choose. It's not they're forced into one. It's just that
right.
they, yeah.
If it's forced to them, then it's gonna be more of a class instead of a club.
Hmm.
Yeah.
All right. You know, I feel like English would be my best subject if like we weren't like graded on based on a rubric.
Yeah. I know.
Yeah.
They restrict it to that rubric to grade.
Yeah. It's okay. There are different types of intelligence. It's just
Mhm.
that I don't know. I spend a lot of my time like thinking or like writing. And,
Yeah.
like
Do
I
you
don't have
journal as
yeah,
well?
I do. I journal.
Yeah, that's good.
It's like, oh, on this day I did this, and then yeah.
Mm-hmm. That's good.
Uh,
Reflect on your thoughts. Reflect on
yeah, it's mostly like yeah. I
see
mean,
what you can do to improve, get better.
mhm. I mean, I don't really have people I can bounce ideas off of, so I kind of just bounce ideas off of myself.
Mm-hmm. Yeah, that's also good. Like spending time by yourself, getting to know yourself. Um, that's like deep, like deep internal. Uh,
Yeah, my junior year, you know, like the most what's it called? Not uh what- I forgot what's it called. Like when you're what's that word? Like when you think a lot, or you're like when you're like I forgot. It's like in psychology. I forgot what that word was. When you're like thinking a lot to yourself, but it's like kind of like let's see. It's kind of like you're doomed in a way. I forgot like but you're like thinking that and it's not actually happening. Existential. Yeah.
oh, existential.
Yeah.
Well, life. Yeah. Mm.
Let's see. Let's see. What was your hardest year in high school?
Hardest year in high school, probably junior year. My junior year.
Hmm. Not surprised. Yeah.
That's when college apps Like, oh no, college dress was senior year, the beginning of senior year, but that's when I like had extracurriculars, wrestling, cooking club, a lot of AP classes to juggle around. Senior year was supposed to be my hardest because I was taking 4 AP classes, was continuing to do wrestling, and also cooking club. But COVID hit, like the lockdown hit, so then that shut down everything.
This is your easiest class.
Yeah.
Easiest.
It turned from the hardest year to the easiest year. March 13th, 2020.
Yeah. I mean, my elementary school was like the first to be hit when I was like got hit by COVID.
Yeah. In elementary school, you were in elementary school.
Yeah, like when COVID hit.
5th grade, right? I think.
Sixth grade, but it was like half of sixth grade.
Half 6th grade. Dang. Oh
Yeah,
yeah.
I,
6th grade. That's crazy.
you probably just played a lot of video games.
Yeah. So I played a lot of League overnight. Yeah, mainly League, but I stopped playing. Like I don't play
Uh-huh.
any video games anymore.
I mean, I told you I blocked all video games
Yeah.
like
At the beginning of the year, right?
yeah.
10 months strong.
Yeah, I don't really have any reason to like download video games ever again, like from now to like this end of high school or like the rest of my life.
Yeah. Instead of like playing video games, instead of like leveling up in games, you can level up in real life.
Yeah. And then like that's like there's also like a problem with that because like I also have school, so I'm like thinking just like sometimes I feel like I don't grow just because like I have school homework and it's just holding me back from like doing other things that I feel like are important.
Right.
Yeah.
Yeah. Good. That's good.
Let's see. Oh yeah, my microbiology teacher introduced us to a hotline for elementary schoolers.
Hotline for elementary schoolers.
Yeah,
It's
it's
like
just like yeah.
you get to call
Uh,
them or something, or they get to call you. Okay. I'm gonna let you go to do sleep, or what are you gonna do the rest of the night, right?
I gotta study for like U.S. history regular, and then here's the hotline for elementary schoolers.
Hotline for lunches. Oh.
Yeah, you could just like it's just a bunch of pre-recorded messages, but like I feel like it might help a lot when when you're just like you don't really have a lot
Struggling.
of people to talk to, but it's just like you don't want to talk to anyone. It's just like you just want someone to comfort you or something like that. So boom.
Right. This is so nice. Like all the cards and everything.
Yep.
Let's see. Wait, did you make some of the cards too?
No, I didn't. It was just like introduced to us by our microbiology teacher.
Huh.
Just like you might be having a hard time, but and then they showed us this and just like
Oh,
oh
and it's the elementary schoolers like giving you a message.
yeah, but this school is in California.
Uh-huh. Oh my God. Have you used it? Have you caught it?
Not yet. I was thinking about it the first time I saw it, you know.
Uh-huh. Yeah. Shoot. Think positive thoughts. You are not the only one who wants to sigh
You could
loudly.
try it. There's not an actual person. It's mostly automated red messages.
Uh-huh. Yeah. We,
Yeah.
we should try it like when we like see each other next time, like tomorrow or like Sunday when we talk.
Yeah, tomorrow. Yeah, tomorrow's like a. I'll get home at like 1 o'clock because like
Uh-huh.
school's out, and and then yeah, and then I have like to 8 hours to study, do everything, and then I get to talk to you again.
Yeah.
Like it's not the final pep talk.
Yeah, the final pep talk with me and the hotline. We're gonna call the hotline tomorrow. That
Yeah,
time.
and then I go to sleep early because
right.
I have like 9 to 8 hours to like study for like 2 classes.
Mm-hmm.
That's good. That's totally gonna work.
Mm-hmm. Okay, yeah, let's do that. I'll see you tomorrow, Ryan. Good luck. Good luck.
Yeah, thank you.
Mhm.
See you tomorrow.
Yeah.
Thanks for the
Bye.
pep talk.
Yeah. Let's go.
Yep.
3,
2,
2, 1.
1.